Okay, great. Welcome, everybody. Thanks very much for joining. It's my great pleasure to be introducing Professor Sarah Gasda today as our departmental seminar speaker. She'll be talking about carbon dioxide storage. This is a key technology central to climate change mitigation plans for all countries around the world, and this is a particularly timely day to be having this lecture the day after we're welcoming the United States back into the Paris Climate Change Agreement. Sarah has been working on issues of carbon dioxide storage since at least as far back as 2008, with a PhD from Princeton University and a postdoc the University of North Carolina at Chapel Hill, but since 2011, she's been a leading researcher at NORSE, a major research organization in Norway working on subsurface fluid flow and pioneering a number of developments in the understanding of carbon dioxide storage underground. So Sarah is the research director in computational geosciences and modeling at NORSE. She also holds an adjunct professorship at the University of Bergen and is leading a research group that is developing the Porous Media Initiative open source reservoir simulation software. If you haven't come across this and are working in subsurface fluid flow, this is a really useful and really innovative tool in modeling subsurface flow. So with that, I'll hand it over to our speaker.
I'll mute myself first before I start talking. Thank you very much, Sam, for that very kind introduction. And hello to everybody out in cyberspace. I'm going to talk about a topic that I know many of you have heard about at Imperial, but I will talk about it from a perspective of the scale up, and also, have some insight coming from the Norwegian side of the North Sea, where I've been working together with a number of partners here in Norway, internationally, Sam included, to really try and push the research towards how we can assess the safe and sustainable long-term and large-scale CO2 storage. But we can't talk about CO2 storage without talking about why we need it. And I really look forward to the day when I don't have to give these slides, that this will be an accepted and very, very normal approach to climate change. But in any case, it's really good to kind of orient ourselves about what CO2 capture and storage is going to provide. And one of the main points is that we cannot achieve zero emissions without multiple climate technologies. I think that is widely accepted. And in the end, we may have to go negative in the sense of negative emissions through the use of direct air capture or BECCS, and then you have to do something with the CO2. We found now recently, especially in Norway, that the cheapest alternative outside of the power sector would be CO2 capture, transport, and storage. And this is especially for process industry, cement, waste industry, and those types of things where CO2 storage plays a crucial role in reducing emissions and otherwise very hard to deal with alternative means. And then, we can't talk about climate change without talking about developing regions and providing access to clean energy where they already have abundant fossil fuels, where CCS can play a major role. And I will point out that the average age of a coal plant in China is only 12 years old, with an additional 40 years of life. So they will likely have to be doing something about those types of energy sources that are already online and very young. Of course, CCS has been brought into the IPCC scenarios. 3 out of 4 of the scenarios rely on significant scale up of CCS by the end of the century. And what I'm showing here is a figure out of that report. Highly recommend everybody have a look at it from a couple of years ago, showing their projections for the CCS growth in cumulative CO2 stored by the end of the century. And really what this is showing is a trajectory is requiring significant scale up of today's storage activity, where we've stored approximately 200 million tons in 2017. But by the end of 2050, we should be up to 100 gigatons. So it's really a growth to fully commercial CCS within a quite short time frame. Our starting point are current facilities around the world. There are quite a few. There have been many pilot demonstration facilities, both in the US, in Europe, in Asia, and Australia, a couple emerging in South America. And the larger scale operations are fewer, but still significant in the breadth and scope of CCS that's occurring right now. But I will remind you that we are still at the very burgeoning stages of CCS, despite the level of activity. So recently, in December, the Norwegian government gave the final green light for full financing, or sorry, not full financing, the government's portion, the public portion of financing for the Longship full-scale CCS project. And this was a major, major milestone for Norway. It is the largest climate project ever, and where the idea is to create an onshore storage hub that will be located just out about 10 miles outside of Bergen on the coast of Norway, that will connect smaller capture projects to a large offshore reservoir. And the transport and storage part of the Longship project is called Northern Lights. And the point of this project in its initial stages is to demonstrate the full value chain of capture, shipping, and storage. And this will be the first of its kind. And the initial capture facility will be located at a cement factory outside of Oslo. The amount of CO2 initially is quite small. It's it's about 500,000 tons per year. But it is a scalable project. They have dimensioned the pipelines and the reservoir to include many more sources in a sort of stepwise approach that can plug into this storage hub offshore Norway. And these are some of the thoughts that Equinor, who is running the project together with Total and Shell, I did not put them on here, and I should, have envisioned the expansion of the Northern Lights by starting to include many different capture sources around Europe. And what they're seeing is scaling in these sources over the next 10 years to reaching 20 million tons per year. But again, I'll remind you that that scale up, it still only gets us to 1 gigaton in 50 years. We need 100 Northern Lights to reach the very first IPCC milestones. So can we mature global CO2 storage? And it is realistic. There have been some studies now going into how to use what we know already about the subsurface from petroleum development of how to reach gigaton storage. This is a paper by Philip Ringrose and Sip Mecco that was published about a year ago that's showing their estimation using some simplified methods, but nonetheless, given the number of active injection wells going in, this is logarithmic scales, of achieving by 2050 numbers on the range of cumulative CO2 injected of gigaton order by 2050. And the colors here are either if we take Texas or we take the Gulf of Mexico, and this is the Norwegian active wells. This is using all active wells that we know and converting them to CO2 storage. And the point of this slide is that gigaton storage can be achieved with less than 20,000 wells, which is really a fraction of the global petroleum wells. And it's showing that if we can accelerate and ramp up petroleum resource development, we can do the same for CO2 storage. But it really also points to the need for optimizing costs and pressure management strategies in these increasingly important regions. So the big questions for CO2 is it feasible and is it safe? And the three main questions are, is there enough pore volume? Will it stay underground? And can we inject it fast enough? And we can answer yes to all three of these questions, and it's been demonstrated already at small scales. But now when we move to gigaton scale, we face some research challenges that for sure need to be answered, and they're mostly on the second two questions of keeping it underground and injecting it quickly enough. So I'll give you a quick run through of CO2 storage. I know you've probably heard about it a few times, but for the sake of orienting ourselves and how we move forward, I'll talk a little bit about CO2 migration and trapping. So the overview picture is you have two phases, and here I'm only talking about CO2 storage in saline aquifers, deep saline aquifers, where we have CO2 and brine. Of course, you can inject CO2 into depleted hydrocarbon fields or into active hydrocarbon fields where you are, but we won't touch that at this moment. You have several components. You have CO2, you have the water, you have salt. And if you have impure CO2, which is likely when you capture CO2 from various types of facilities, or you're injecting into depleted hydrocarbon, you can get many more components and phases even. CO2 is injected as a supercritical phase, and that's important because it is a dense phase, and that is increasing the storage efficiency. And if you look at this plot down here, you can see that you get a 98% reduction in volume for the same amount of mass as CO2 is moved into a supercritical phase, and this is with depth. And it typically occurs around 800 meters depth into the subsurface. On this plot, as we move up in pressure and temperature, we're moving through the phase diagram for CO2 and into the supercritical region. And supercritical fluid is an interesting fluid. It's neither a liquid nor a gas, but it has properties of both. It's a very dense liquid, but it has sort of fills the volume like a gas would. So densities are on the order of 400 to 900 kilograms per cubic meter, still less than the native fluids. And the viscosities are also significantly higher than CO2 as a gas phase in the atmosphere, but still a factor of 5 to 40 less than brine. Rock properties are typical for petroleum type of reservoirs, with permeabilities ranging in the tens of millidarcy to several darcy, with porosity also in an acceptable range. So the main processes are really at work in how CO2 migrates and is trapped eventually are related to a variety of different processes of flow, capillarity, dissolution, phase equilibria, et cetera, et cetera. Geochemistry and geomechanics also play a role. And the goal is to really keep CO2 from leaking most effectively by transforming it from its free, unstable, buoyant phase to a more stable phase. Geology plays an important role, both at the large scale and the small scale. So here's the slide that's showing a bit, and of course, taking a lot of these figures from my colleagues in Imperial College of multi-phase flow processes affecting the flow. And this is we have to start at the small scale to understand how things move at the large scale. And this goes from capillary pressure and Longterm measurements and really interesting pore scale imaging, to the effect of lamina and deformation bands on how these capillary pressure functions look like, and then thinking about heterogeneity at a slightly larger scale and how that will affect the CO2 plume and how it migrates. So capillary pressure already at the very small scale even, and its heterogeneity has a role to play in how CO2 migrates, either through anomalous migration or creating compartments for CO2. Some of those are not desirable effects, so we need to understand them. At the sort of structural geology side, that also has an enormous effect on flow. This is showing, of course, a real outcrop, I think, in Utah. And this is an effect we already see in the Sleipner CCS project off coast Norway that's been going on for 25 years, where very large scale baffles, so scales on the order of kilometers in extent, are creating a layering of CO2 at the Sleipner field. That has a good effect in that it helps increase reservoir sweep and reduces the up-dip migration speed, but it's something that was not predictable from the beginning because they're subseismic. The cap rock itself has an extremely heterogeneous role to play, and CO2 doesn't have a radial plume as it normally would, as it would be expected for a flatter cap rock. And here, cap rock heterogeneity and cap rock roughness can affect the up-dip plume speed, and this can be looked at from the perspective of upscaling rel terms. And all of it comes down to there's a significant amount of uncertainty, especially before you start to inject CO2, of what these effects might be and how we can predict CO2 migration. As we move into CO2 being trapped, this would be processes that occur after the injection. They can occur during injection, but they're more likely to be a bigger role after injection of residual trapping of CO2. This is a standard process, of course, from petroleum we know a lot about, but it plays an enormous role for CO2 and how much CO2 is left behind as this plume moves away from where it originally was injected. There's a good deal of uncertainty on how much CO2 is really trapped, and that, of course, is an active area of research. The main trapping mechanism, especially at the beginning, is the cap rock itself, which is tends to be a shale or mud rock or some other regional seal. Capillary sealing has to do with the change in pore throat size as you move from the reservoir rock into the cap rock. And the sealing capacity has an important role to play in predicting how much plume height can be supported by this cap rock. And it's, some simple estimates can give you a pretty good idea of the height of CO2 that can be supported. Over time, there are effects that occur due to the CO2 dissolution. CO2 dissolution actually increases the density of the formation fluid of the brine. It's not a very large increase, but it is known and can be measured in the lab of how much CO2 is being transferred from the CO2 plume into the brine as a dissolve phase and creating this unstable density profile that then convects and enhances dissolution. So you can get dissolution rates that would be upwards of 10 to 20 kilograms per square meter per year. So this is can be a significant effect over longer periods. So this is the picture of these trapping mechanisms and how they contribute over time. From the short time scale, you know, the first 50 years, the first decades, most of the CO2 remains as a separate phase where you have this gravity and viscous instability that's that needs to be contained by the cap rock itself. So you're very reliant on the cap rock. But then over time, these other mechanisms take over, so that by 100,000 years, you expect that a lot of the CO2 will be in more stable forms. Residual solubility or mineral trapping tend not to go too deep into the 1,000-year time scale, but there are some highly reactive systems, especially volcanic rocks and basalts in Iceland, off the west coast of the US, where CO2 is injected and it's fixed as a minerals phase in very short timescales, and this has been demonstrated in the field. Okay, so I'll walk you through a little bit of a larger scale case study of how these mechanisms interact together and how we think about the long-term migration. This is an older study now, but still relevant because the Johansen formation is in fact a target formation for the Northern Lights project, although the simulation was done before Northern Lights was even a concept yet. But it's interesting just to see a little bit about how the mobile CO2 after hundreds or even 1,000 years will evolve where residual CO2 is, and this is looking at a plan view, and how much CO2 is dissolved by this kind of convective mixing. And this is these scales here are in thicknesses of meters, so it needs to be translated to mass, but you can see how over time there's a significant depth of the vertical space that's covered by dissolved CO2. And very little now, very thin CO2 plume is sitting at the top that's essentially trapped by the structure itself. Oops. And if you can see the distribution for this case, in this case, you're really relying on the cap rock. This scale is 2,000 years. So the first 100 years, the cap rock is really 95% of the trapping is provided by the cap rock. So although these other mechanisms are extremely important for fixing the CO2 in a more stable state, it takes time for them to evolve. But at the same time, the CO2 plume is moving very slowly. It takes 500 years to move 10 kilometers. This is a very low permeability system relative to, it's not Darcy, it's hundreds of millidarcy. But still, it's a slow evolving system. And the other thing to remember here is very difficult to determine exactly what's going to happen over 2,000-year time scale and 10 to the 6 square kilometers. So it's not a reliable prediction, but it's giving you an idea of how these processes are coupled together. But it's also important to think about the sensitivity to the fine scale. So going back to what I was talking about a minute ago, subscale heterogeneity, compartmentalization, for example, could in fact lead to less dissolution because the CO2 plume doesn't move as far, it doesn't contact as much brine. Whereas anomalous migration, although it may sound less desirable, could actually contact more brine and increase the dissolution. So how these different subscale, very fine scale processes impact these very long, large scale behavior is still a subject of inquiry. Same thing for residual trapping. We don't know what the land's residual trapping model really looks like for the Johansen. And it will also have an impact on plume extent by increasing or decreasing this light green. more or less contact with the new brine, more or less dissolution. These are questions that still need to be looked at, especially for these large-scale systems. The same thing for convective mixing. We know that that these rocks are not perfectly homogeneous. They could have baffles. In fact, we do know that the Johansen does have some baffling that could reduce convection by spreading out the fingers and not allowing them to freely convect, thus reducing dissolution. Then you have more reliance on residual and structural trapping. Okay, I'll flip a little bit gears into pressure and mechanics, because as also at these large scales, and I'll just remind you that none of these simulations that I've showed a second ago, they of course are modeling pressure, but the pressure wasn't the main question back in 2012. In the last 8 years, pressure has become a very, very significant area that we need to get a handle on. The main reason is because of mechanics, and this figure is also from a couple of years ago, 2012, right around the same time that pressure was emerging as the big question for the researchers, showing all the scary things that may happen. And not because it should be alarming, but just so that we need to be aware of the role that pressure is playing in the mechanics of the reservoir, the potential for fracturing near the well, the potential for reactivating existing fractures or faults, minor faults, major faults, and the potential for inducing seismicity. And here, induced seismicity, we should really be the potential for inducing felt seismicity. Induced seismicity is something that happens all the time in the subsurface. Things move and they make noise. It's the felt seismicity that would be the concern. Whoops. So the injectivity at the wellbore is the first sort of line of defense. You want to, when you're injecting fluids, you want to protect against fracturing the reservoir or the caprock where the pressure is in fact highest. The injection rate is ultimately limited by the so-called fracture pressure. However, it is estimated, and I'll talk about that in 1 second. But you can, because it's the wellbore, because that's where most of the monitoring in fact is going on, you can get a quicker control of when you're close to the fracture pressure or not. And that can be due to, salt precipitation can cause a problem there. You could have a limited extent of permeability zone, permeable zones. A variety of things can happen at the injection well that can cause injectivity problems. And there are solutions that vary from treatment to horizontal wells to improved characterization. And this figure is just showing you some laboratory results out of our institute down in Stavanger that show that CO2 causes the pore space to dry out in the region around the well. And when you evaporate the water, you leave behind the salt, and that salt precipitation can reduce porosity and permeability. So this is shown experimentally, but it's a manageable problem. But if a fracture happens, you can actually do something about it, or we're trying to look at ways of doing something about it and stopping leaks when they're discovered. We actually have a project here where we're looking at using microbial processes to generate cement in situ. And this technology is called microbially induced calcite precipitation. It's been demonstrated at the lab in the field. And really, it's the engineering scale where the gaps are and how to model these quite coupled processes of the correct scale. We have a new paper, actually, where we're looking at porosity and permeability reduction on the order of, the scale here is on the order of meters. This is not a core. This is a radial view of a reservoir where we've looked at techniques and strategies for creating a kind of zone of blocked off pore space that then things can now flow around and they wouldn't leak upwards. But anyway, back to injectivity. The other big concern with injectivity is faults. Fault reactivation can occur due to reduction in effective stress, which can cause dilation and slip. I'm not a fault mechanics expert. This is what I've been told. But reactivation could lead to leakage and induce seismicity. And this is a figure from a former colleague now at University of Oslo, Anita Tarabi. They've done a lot of work looking at faults in the field and trying to get a handle on what the risk is for leakage along faults. Microseismicity can also be generated. I mentioned that a second ago from the fracture simulation at all scales that aren't even related to major faults. And here the solution is to really characterize the faults and keep the pressure at the fault below the critical pressure. And the critical pressure is, of course, a huge area of research of understanding the fault characteristics, dip and strike, the stress field, etc. To know what the pressure limit really is there. So determining maximum pressure, enormous area of research. It's not in my field, and Adriana, I think, could probably say much more about this than I could. But so mitigating fractures in intact rock is, again, sort of first line of defense. The tensile strength of the rock, you can get these measurements from leak-off tests or extended leak-off tests. I mean, what you're really trying to do is understand the minimum compressive stress, and it's sometimes very simple engineering solutions to percentage of vertical stress, just showing you some leak-off pressures from the North Sea, where we were trying to come up with a decent model for the change in the horizontal stress with depth. And of course, here's your hydrostatic stress or hydrostatic pressure, and this arrow showing you the window you have. And this applies anywhere in the reservoir. Remember that it's not just near the injection well itself. And so your window decreases as you move shallower. So if parts of your reservoir are shallow, then the window you have there may be lower than actually where you're injecting. Fault stability, your standard Moore-Coulomb analysis, and again, it's dependent on the stress field, but it's also very dependent on what is the pressure change at the fault. And that is not an easy thing to understand because faults are extremely complex. The geology and the damage zone around the fault. And we have projects now where we're really looking at this together with geologists, modeling, simulation, to understand how fluids approach and interact with the fault core itself, which is where the largest risk for a slip is. Okay, so when you move to larger scale injection, given a lot of these details that I flew through in 25 minutes, is really about sustaining injectivity. So yes, you can get injectivity problems, you can resolve them. Yes, you may know what the injection, what the pressure at the fault, let's say you know all of that. You still now have a ramping up of CO2 injection. Think the Northern Lights project. Within 10 years, they want to increase injection rate 20-fold. Right, so how would that system react? And so here, injectivity really now is about sustaining what is a good initial injection rate over longer periods. And now you start to have to think about the very large scale features of your system. You can call it a storage complex, you can call it the basin scale, you can call it, it depends on where you are. If you have a very open system where fluids are free to just move, then this type of pressure rise, a long-term pressure rise, even with scale up, is less of an issue because you get it takes sometimes some years, but you get a eventual decrease of pressure as the system is just easily dissipating and brine starts to move and this pressure pulse moves away unhindered. Of course, in an ideal world, that could happen, but not all systems are like this. But there are many systems that have a very free, you may be lucky enough to have an outcrop at the ocean, as is the case on the Endurance, where you know the chance of keeping your pressure down is greater. If you have a closed system, then it flips the other way. And here you'll have a pressure rise that will continue to increase. How long it takes when it finally gets there is of course up to the larger scale boundaries. And there's a lot more uncertainty, and it's difficult to forecast these things. You could have a semi-closed system, again, more likely to have somewhere in between open and closed. And then native brine can move through the caprock, because the caprock, although it's very low permeability on the order of micro to nanodarcy, water can still migrate there. But in any case, the pressure in closed or semi-closed and even an open system eventually will have to be actively managed sooner or later. We have some field experience with injectivity already. The Snøhvit CCS project, which started in 2008, similar to the Sleipner, and I won't go into the history of CO2 injection on the Norwegian continental shelf due to Norwegian carbon taxes on offshore emissions. But in any case, CO2 has been injected at Sleipner for 25 years, and at Snøhvit they've been doing it since 2008. They initially had chosen the Tuboen formation. They had characterized it, they had drilled a well, and they started injecting, and the pressure was rising. And we know the pressure can rise initially until the dissipation starts to take over. And they waited and waited and waited in a couple of years, and the dissipation mechanisms were not taking over. They thought they had self-precipitation, they did some treatment, But after 3 years, eventually they decided that what they really had was uncharacterized or undetected compartments or subseismic faults that were creating barriers enough that they were never going to achieve the sustained injectivity. It was not all lost. They recompleted the well in a different zone, and they continued to inject since then. So the project itself has been fine, and there was never any risk of fracturing. But this is a very good example of how this fracture pressure is an important thing that needs to be understood in advance. So the challenge is really now in moving to gigaton deployment, and we've never done the gigaton deployment, is driven by both this pressure and managing pressure and sustaining pressure over the long term, but also CO2 migration and trapping. And I'll explain a little bit about that in a second. We need to unlock new storage sites in different geological settings, and this is related to the first point. Optimal sites that are open, that have all the right traps with no uncertainty or little uncertainty will be taken up by the first movers, and we need to already today start de-risking and understanding the more challenging sites. Managing regional pressure buildup is, of course, critical, and I've talked about that. And in addition, we need to provide a convincing picture to the bosses of the guys that we talk to stakeholders, to regulators, to politicians, to the public, that CO2 storage is a low risk and effective climate technology at these scales. Luckily, we've had lots of workshops and discussions in the research and CCS community about what is needed. We have research directions. We know what needs to be done. This has to do with our ability to understand the physics of multi-scale fluid flow at gigaton, the dynamic pressure limits, and characterization of fault and fracture systems. I won't really talk about the third one, but just so that you know. Okay, so forecasting storage performance. This goes to what the setting is. So you have the conservative choice, which I call the conservative choice. It's the good, let's say the good reservoirs. It's a bad word to use. The first choice for many operators right now is structural open traps filled to spill. Mostly all you need to worry about is the seal integrity of the caprock, and that can be demonstrated fairly easily in a number of ways. You may have regional hydrocarbons in the vicinity, you know, lots of things that you can do there. Classic 3D fluid flow reservoir simulation is completely sufficient to understand this system. You fill the spill, you close the well, you walk away, and you let the rest of some mechanisms will happen. You'll get some CO2 dissolution at the bottom, and we know the CO2 can remain in this. It's an unstable phase, it's buoyant, but it can remain there for millions of years because we have lots of examples of natural CO2 reservoirs. In the Western US, there are Bravo Dome and Sheep Mountain and what have you. So this is a perfectly good choice. It's definitely the easier of all of them. Then you move to B, which is what we call migration assisted storage. And the global storage potential of B relative to A is enormously larger. Right, so A you'll run out of quickly. Here the scales are larger. CO2 moves farther. You're really reliant. This was the Johansson. You're reliant on the residual and dissolution trapping. Uncertainty plays a larger role. You may need temperature. You may and everything starts to compound. And fluid flow simulation, the classic way of doing it, is not suitable anymore. Computationally too expensive. The wrong scales. Various things. So you can do a couple options. You can do a lot of rigorous upscaling, and that should be done and is being done. Extremely computational intensive. And in the end, you can't include everything. You may have to take some shortcuts. Modeling 2, again, you have to take shortcuts first and thinking about how to hybridize and modularize your approach. There's a lot of existing things out there, but they aren't really implemented for CO2 storage. And you really need to retool a little bit the simulators, and benchmarking is a real challenge. So I'll look a little bit at what's been done. The Illinois Basin is one in the US, mid-continent US, is a large storage resource in the Mount Simon sandstone that has had now 2 pilots looking at the potential for CO2 storage there. But there have been lots of studies done, or several studies done on large scale, deployment of CO2. And this is one example of out of Lawrence Berkeley National Lab, where they set up how many wells are here, 20 wells, and injected CO2 and looked at the large-scale pressure plume. So as opposed to the Johansson formation I talked about earlier, where we only focused on the CO2 migration and trapping, here is all about pressure. I think Chicago is somewhere up here. I think that's the lake. And you can see the pressure plume is enormous from this type of injection, 50 years of injection. But the pressures themselves aren't, because it's a very big, porous, permeable system. And you can see here, they're the pressure plumes. They'll almost look like, yeah, polka dots on this picture because the scales are on the order of 500 kilometers on the side. And what they've shown here is that, you know, you end up in these systems because they are so large. The characterization is not really available to do anything more than mean values for rock properties. The resolution of the data, a few wells is very low. And then they weren't even able to do the post-injection plume migration and long-term trapping. So these plumes at 50 years, we just have to be confident that they will be eventually trapped. So because the focus in this paper, of course, was on pressure. But in any case, these were intensive simulations. So running a 50-year simulation, another 950 years, was probably not in their budget. But there has been some work done on pressure management using more simplified methods. This is work out of Princeton. My former group, Carl Bandilla and Mike Celia, and there they were looking at the same formation and targeted brine production. And brine production means now drilling new additional wells to remove the same amount of volume of brine as you've injected CO2. It can be quite effective, but it imposes a cost and imposes another problem of what do you do with the produced brine. Reinjection induces another challenge. But in any case, you can at least manage the pressure in this way, and then what you do with it after that and the cost is another story. Again, relatively simple simulations, same idea, mean properties, not a lot of geological heterogeneity here that could affect how well this system can be managed. In the North Sea, there's been also a few so-called capacity studies trying to understand how much CO2 you can stuff into very large-scale systems. The CO2 Storage Atlas has identified a number of potential storage resources. One of the more popular ones to simulate on is the ESE sand because, well, first of all, the Schleipner injection is in the southern portion of this formation. And I'm showing you 3 different studies. There have been a couple more, I think, looking at trying to estimate the capacity through trapping mechanisms only with, open boundaries. This should be, so no pressure. Here was water production with CO2 being injected on some kind of checkerboard with no desire to understand how the trapping is happening of the CO2. And you can see already the estimates of storage are ranging from 1 to 100 gigatons. I did a study with some colleagues looking at trying to combine CO2 migration with pressure and also a simple model for uplift and trying to, I would say optimize is not the right word, but trying to get some handle on being able to effectively trap CO2 and handle pressure. And again, we can't do this with the Eclipse. We have to use very simplified, but still trying to couple as many of the important processes together to see how this, in this case, 5 gigatons can be injected into the southern portion of the ESE. So there's a lot of uncertainty here, and it's sensitive to what you're assuming. It's sensitive to how you're modeling, and which one is right. That's still an open question. So this is still work that needs to go on. So I'll kind of start to close here, but with how we are thinking about tackling the large scale simulation. I'm showing you a little pieces of everything I've talked about, from millimeter scale, pore scale, phenomena that are affecting, at least field scale ways of CO2 migrating, field scale phenomena, baffling, all the way up to the size of the grid blocks that we're using in these simulations that I've showed you at the large scale, 3 by 1 kilometer. I think this is correct, the size of Hyde Park and Kensington Gardens combined. Enormous grid blocks, and this is a major challenge. It's a major challenge not just in CO2 storage, in all fields of subsurface investigation. Moving from millimeter to kilometer is not trivial. Lots of work has been done, very valuable work, and much work still needs to be done to understand which equation should we really be solving here? What are the constitutive functions that takes into account the multitude of things that are happening at the very fine scale, or even not so fine scale. I won't go into this. We're thinking about this. We're writing proposals on this. We have projects on this. Sam mentioned OpM. I'm embarrassed I didn't have a lot more on OpM here. OpM is an open source reservoir simulation tool. It's a lot more than that, but the most popular thing that's used is the so-called OpM Flow. It is a, let's say, Eclipse emulator in many ways. So those of you who've used Eclipse or other standard reservoir simulation tools would be very comfortable using OpM. Use the same input file as an output. So we had this tool that we've been working on for a long time, and over the years we've been, of course, transforming it, and as the oil industry is doing, into CO2 storage. We have a new project where we want to kind of, I wouldn't say retool is the wrong word, but we do want to make OpM Flow, or at least a version of OpM Flow, be a dedicated CO2 storage simulator. And this is with many things in the oil and gas industry that they're migrating from oil and gas production exploration to CO2 production or injection and exploration. There are things that we can actually reduce and simplify from the oil and gas industry, but then introduce new complexity at the CO2 storage. So in this project, this is what we want to do. We want to create a dedicated, and the number of dedicated CO2 storage simulators out there are few and far between. And then we want to make the leap at the same time to being HPC capable, which means really being able to tackle these very large scale systems, and then also have the opportunity to retool where we find it's best to be able to handle the specific things that are being thrown at us with gigaton storage that we don't normally see in oil and gas. So this is work that's ongoing. I don't have anything to show right in the minute, but we're really trying to push the boundaries. And we're not the only group to do this. Lawrence Berkeley National Lab, or sorry, Livermore has come out with a similar type of approach, but with really the focus more on the geomechanics. I'm not getting the name of that simulator off the top of my head right now. And there's also a small startup company in the UK, OpenGoSim, that have their also based on pFlowTram simulator that they're also trying to. So there's a really new and very exciting push towards really pushing the boundaries of simulation for CO2 storage. So I'm excited to see where we go, where we end up. Okay, I'll skip that. So a couple minutes, the summary and outlook. It's those of us who've worked in this for many years, CO2 storage we know is viable. There are demonstration and industrial projects going on, have been running continuously with no problems. You know, no problems being there has not been any climate related problems. Of course, there's always engineering problems that need to be solved along the way, and that's how all engineering projects are. Research has solved many aspects of CO2 storage risk. It's been amazing to see you know, how much research has been done has been taken up by industry already in a quite short period of time, and that's really exciting. But new challenges really await us as we move towards very climate relevant deployment of CO2. So we need to continue the bench scale studies, focus on upscaling. I did not talk about wellbore integrity, fault seal integrity. These are very important. And I also did not talk about monitoring because monitoring technology is really how we catch problems when they arise, find solutions, and then use monitoring data to calibrate models, improve what we're doing on the modeling and simulation side. So that's an enormous field in and of itself, but it's extremely essential. So then I think I will stop there. and thank everybody, and look forward to your questions.
Okay, excellent. I don't think, can you hear me? Okay, I don't see the live figure on these. So excellent. Thanks very much for excellent presentation. I have heard that we have over 80 participants in the seminar, and we do have a good number of questions coming in. So I'll do my best to get through them. So we have one group of questions that have come through about the scenarios you showed for structural trapping versus making use of residual trapping in the storage project. So coming from Rosie, there has been a pilot project, no injection yet, but core seismic modeling in West Australia, but no seal. Very thick sandstone package, however, more like your choice B. What are your thoughts on such a project's merits? And related to that is one coming in from Anonymous, which says, with CO2 pricing, isn't the risk that companies go for option B, but don't bother too much on long-term effects?
Okay, so the first question was about the merits of, I didn't understand, was that, I don't know the Western Australian project that's actually being referred to. Is it the Gorgon? No, yeah. They have a seal. I mean, all CO2 reservoirs have to have a seal. That would never, yeah.
I think that the question is really, and both of them really coming around to what are the merits of a project which doesn't depend on a structural closure, but rather will require this the use of this residual and dissolution trapping to secure the CO2 underground.
The merit of a project. I mean, I think it really it has to do with the point that I think the merit of such a project is that you have a better chance of getting the CO2 out of this unstable phase. You know, if you keep it in a structural trap, it will sit there for millions of years as a CO2 phase, and but it has many advantages. That it's contained, it's a smaller area, it's, let's say, easier to monitor. But if you let the CO2 go and migrate, then it moves into these stable and more permanent phases, you know, residually trapped, dissolved, and eventually mineralizes. So unless we have some interest in reproducing that CO2 again, there's no need for it to keep it there in this bubble and let the system re-equilibrate. You know, you're creating a disequilibrium in the system with a structural trap, but there's many attractive things to the structural trap from a cost, operation point of view, why they are choice A. And, you know, Sam and I know this from talking to various operators that, you know, it's harder to get the, because there's more uncertainty in option B. There's the larger scales and things, so yeah, that helps.
Okay, so now we have a question coming in from one of those organizations. So Tibi Sarup from Shell asks, the issue of induced fracture during injection is well established in water flooding for oil industry, including modeling and surveillance. Is that knowledge leveraged well enough? Are those industry tools for modeling and surveillance being used?
I mean, in industry, I can't speak for what's being used, but I would say yes, of course. I mean, all knowledge that in workflows that are established in industry are, to the extent possible, used for CO2 storage. It's just that the few projects we've had that the community has had with injectivity issues, they were solved by standard industry practice, monitoring the pressure, trying a few treatments, and then moving on when they realized that it wasn't going to. So I didn't want to paint injectivity as a major issue, but it is something that, of course, is not. It needs to be looked at, but it's one of the more relatively straightforward ones to solve, I think. Local wellbore injectivity.
Okay, great. So there are a couple of follow-up comments actually that I'll mention. So Rosie followed up mentioning that she was referring to the Southwest Hub. There are no seals. but baffles in the sand, and the plan is to inject and rely on plume migration. And then Owain from Shell has mentioned that Quest is migration-assisted storage and has injected nearly 6 million tons to date.
Yeah.
I'll go on to another question. Feel free to comment on any of that, of course. So Professor Matt Jackson is asking about modeling. So other areas of computational fluid dynamics use varying mesh resolution to reduce the cost of capturing transient fine solution features in a large domain. Have you considered this?
Yeah. Yeah, so mesh refinement and adaptive mesh refinement. No, it's something. It's not a standard computational practice, of course, in reservoirs. Adaptive grid refinement is not something you find standard in commercial reservoir simulation. So it's more difficult to implement, has its challenges. But yeah, we've looked at it. I just don't think it can solve all of the problems, but I think it's one of the tools that you should have available for it's a particular region that you identify early on or along the way, that where you would need to have more refinement as the only way to. So the large scale and upscaling is not supposed to be replacing fine scale simulation. It's just one of the tools that we need to be able to develop reliably, and then coupling, but moving back and forth between scales as needed is something that will have to happen regardless. And I'm sorry, Owen, about Quest. I forgot that it's migration assisted. Good.
Yeah. Okay, so then we have, I'll group a couple of questions around the very large scale issues. So coming from Matt, a different Matt, thanks for the nice overview of potential for CCS. You touch upon brine production as being expensive. Do you think the 2050 goals can be met without brine production? As in, are there sufficient reservoirs available which could store carbon dioxide without brine production? And related to that, coming from Dan, is what are your thoughts on the best way to deal with the trust issue? How do we get buy-in from stakeholders we need to get to the gigaton scale?
Yeah. Yeah, I mean, brine production can be done more cheaply, and I think there are many. There are areas where brine production will need to be, not because of pressure management, but where you want to maximize the trap. So the fill to spill situation may even require brine production, and I think in the endurance that's one of the long-term plans there. So it's into the development thinking. But if you take the North Sea, I mean, the North Sea has quite a lot of very nice permeable reservoirs that can probably take a lot of CO2 without brine production within 50 years. So I think it's regional dependent, and it's certainly something that every site will need to evaluate. But I think at the resource assessment scale, finding ways to minimize the number of brine producers if you are going to have them, and coordinate it. And because of course brine pressure doesn't have an owner in the same way. If you have multiple sites operating in the same region, the pressure won't have an owner in the same way the CO2 will. So there'll have to be probably a more collective approach to managing the pressure so that everybody can sustain their injectivity and not just the first guys out. But that's certainly a policy maker's question. But we still need the tools to be able to design such strategies and rely on them. And then the second question was.
It was about the trust issue. How do we get buy-in from the stakeholders to get to the gigaton scale?
I think it's first understanding what they perceive. Oftentimes, what we think from the storage side and from those of us who are very technically involved, what we think are the risks or what we think are the big challenges aren't the same as what other stakeholders are perceiving. And I guess if we go back to the Quest example, where it's worthwhile to put in monitoring that from a technical standpoint may not be necessarily the first thing you would choose, but from the societal standpoint, you will have it because you want to build that trust that you're listening to what their concerns are, and you can't explain them away from the technical side all the time. So I think you have to be willing to relax a little bit from the technocratic viewpoint and engage the stakeholders early on to understand what their viewpoints are.
Okay, so there's a question coming from Dan about data, and the question is, has there been any thought on how knowledge and data can be shared as CCS projects ramp up? Will Northern Lights share their data so we can learn from each other and so we can be most efficient in scaling this up?
Yes, Northern Lights has already shared what they have. All the well data is available. Those who get in contact, I think the universities are actually storing. I think UIB has storing the data at the University of Bergen. So yeah, they're being very open, and open data is extremely important. There's an open data share project up and running in collaboration with Syntef and Equinor, sharing data from the Decatur pilot, seismic data, Schleipner benchmark data, yeah, seismic data from the Schleipner, well, maybe not seismic data, but at least some models there. So it's definitely a movement towards openness. Mm-hmm.
Okay, and then we're coming back around to the question around the use of residual trapping or the migration assisted storage. And Ruben wanted to know specifically, isn't the risk that companies go for option B, so making use of the residual trapping in migration assisted storage, but don't bother too much on long-term effects?
Yeah. I mean, I think that comes down to a regulatory question, right? So and when you hand over the site, because that's kind of the model now, is that there's the operational phase, and then there'll be a closure phase that the operators will be liable for, and then eventually be handed over to the state, at least from what I understand so far. So they may be forced to consider some long-term effects, at least to a certain degree, to meet the regulatory requirements, for that they're demonstrating prior to handover that that they are confident that the residual trapping and the dissolution and whatever will, within some uncertainty, acceptable uncertainty, will take over. And how long that window needs to be before everybody's happy, that of course will be site dependent. So if we take the examples I was showing, Johansson, I mean, you know, it probably within, I'd have to go back and look again, but you know, probably within 5-10 years of monitoring the post-injection phase, that you'll be able to have at least some better ideas about how much residual trapping there is and dissolution and various things. So I think those are things we do need to think about, of helping companies provide the information they need to hand over sooner, not too soon, but appropriately. Mm-hmm.
Okay, so we'll get one last question in, and this is coming from Ross. Is there a preference for clastic storage sites over carbonates?
There's definitely a preference for clastic. But again, I think this
is that your preference, or is
but why? I mean, carbonates are more heterogeneous and more difficult reactive issues there. But carbonates are in Eastern Europe, for example. There's going to be a pilot in a carbonate reservoir in Czech Republic that they've been developing. So it will be highly regionally dependent. But for sure, North Sea, I think plastic will be the first options, from what I've heard.
Okay, well, excellent. Thanks very much for that. Thanks very much for the great presentation and discussion. And with that, I think we'll end the seminar.
Perfect. Thanks, everybody.